So Yuvaraj is a senior research engineer and embedded lead at AI Shield. With over a decade of experience in embedded systems, he's currently leading embedded AI security research at AI Shield. His experience spans across domain, including automotive and industrial IoT. His special interests are time series, sensor data analysis, and tinyML. AI Shield is a corporate startup of Bosch with a mission to secure AI systems of the world. Looking forward to your session, Yuvraj. Over to you.
Thank you. Thank you for the introduction, Aruna. Good morning, everybody. I'm excited and I'm glad to be presenting at tinyML Asia this morning. I would present on the topic attacks on tiny intelligence this morning. I would like to bring a security perspective to tinyML. To start with, I would start with addressing the tiny devices. So when we say tiny devices and tiny machine learning, we have seen the classification, the characteristics of tiny ML devices and their number, especially in comparison to other platforms, cloud and mobile. The number of devices or systems that we have on the field are significantly higher and are only projected to be higher in the next coming years. We have had tiny devices in the past in the name of edge computing with or without AI for various applications, including wildlife monitoring, agriculture, smart factories, and so on. These devices have been deployed in open environments like fields, factories, and public spaces, and so on. So these devices were prone to security issues, prone to attacks. We have also these devices, because they are in the open fields, as an attacker, one would have full access or the hardware access to the device, unlike a cloud where it is in a completely secure enclave, for example. And when a device is stolen, it is always not possible to detect if the device is stolen, if somebody plugs the power of the system and so on. And these devices are prone to both software and hardware kind of attacks. We have seen several security threats on these tiny devices, and we have had traditional embedded security to protect them. So one of the sections include the device protection, the protection being on the device itself. For example, the readout protection in STM32 controllers would come in multiple levels, where one would want to protect the registers or protect the complete device as such. Some of the subcategories in the device protection included memory protection, software isolation, interface protection, and system monitoring, that in runtime, if there is tampering or abnormal behaviors, one would be able to then detect that on the device itself. In addition to that, we also had security applications on top of these devices, including secure boot, secure firmware updates, secure storage, and additional crypto services to add on. These protections have been there in the past on these tiny devices. Now, with the possibilities, more and more applications, use cases that we are able to deploy more and more machine learning and AI applications on these tiny devices, we also enter into this new perspective, and which is an important perspective to look at, would be the adversarial machine learning. I would like to give a short overview and on the different kinds of threats that are possible, or the attacks that are possible on traditional AI systems as such. Some of them include poisoning, extraction, inference, and evasion. So in poisoning attack, so an attacker would inject malicious samples into the dataset, which when used to train the model creates a backdoor or affects the retraining process itself. Another interesting and very important attack is model extraction. An attacker could probe into a machine learning system in order to reconstruct the model and thereby stealing the functional model itself and or stealing the IP and the functional model that is inside. Another important and interesting attack is the evasion attack. So an attacker for a given input that is going into the machine learning model can add perturbations, calculated perturbations into the input to evade the system in order to create a misclassification if it were a classification model, or to change the output of the system if it was forecasting or a regression task in order to create a specific system impact on the model's output. In addition, in an inference kind of an attack where the data involves personal information, the attacker attempts to determine if the information is part of the information is from a person that was part of the training data or not, for example. So going ahead, I want to focus on two major attacks, which is the extraction attack where the model itself is stolen, and the evasion attack where somebody adds perturbations to the input in order to create an adversarial output. Bringing the classification into perspective, use cases, for example, from the autonomous driving domain. For example, on the left, you see an example of a model extraction attack for pedestrian detection algorithm from a traditional AI model. The original image here, the human label data set, the prediction from the original model, and once the model is stolen, the model's performance. So when the model is subjected, when the model, the stolen model has this particular output, so which is very close to the original model's prediction. So that is what I mean by a functional equivalent of the original model itself. Another attack here is the model evasion attack, where this in general, the first block here, first image here, which is a stop sign. A human can detect that it is a stop sign, and a machine also detects with a very high confidence that it is a stop sign. Once we bring certain perturbations, as we call it, targeted in the original image, then the machine can no longer detect this as a stop sign anymore, and the confidence goes down detecting this into as some other class, and hence leading to more consequences. So the framework of model extraction, how does it work? Given a trained model, F trained using a proprietary data set is given access to the user is able to give inputs and access the output and so on. Now, an attacker would have a query engine through which he will be able to generate a query and choose specific queries that he would want. And he would query the model F the same way that a user would do and obtain predictions. After several querying, he builds himself a learned label dataset, which is then used to train a replicated model or a stolen model, FE. This model is then the functional equivalent of the original model. How does a trained model react to such a query, and what are some of the examples of such a query? Such a query can be as simple as a random noise. In image use case, if the attacker were to attack a model that is trained on an MNIST dataset, the attack query for a simple noise-based image would be something like this. This is pulled out of a pure Gaussian noise, and when that is fed to the model classifies this as label 8. So the attacker then can craft more such examples, use them as queries, and get more and more predictions in order to create or train a new model, which is the functional equivalent of the original model. In the second kind of attack, the model evasion attack, the attacker would add, like I said, a small calculated noise in most cases in order to misclassify a specific classifier. And some of the commonly known evasion techniques are usually are very predominantly used in the adversarial ML domain itself. For example, the fast gradient sign method. So there's this input X, and the attacker adds this perturbation where the epsilon equals the attack strength, and creates an adversarial input X tilde. Now this in the image, this being the original image, and this is the adversarial, the term that you see on the right hand side, creating the adversarial image, which is the sum of these two. And the adversarial image for human would be as close to the original input. Now this input when fed to the system is misclassified not anymore as a panda, but as a different class. And similar examples can be shown on the MNIST dataset as well, that adding minor adversarial perturbations makes the model misclassify the original examples as incorrect examples. Now we have seen the tiny devices, how AI security, how the embedded security, the classical embedded security has played its role to protect those devices, and also have seen the adversarial machine learning part of it. Now bringing these two together, when an artificial intelligence is deployed on a tiny device, and when we subject them to such AI attacks, how would it look like? So we consider an attack setup. In this case, I would like to take two examples. This example starting with the time series classification, the very known gesture recognition, which is the magic wand using IMU, with an ESP32 board connected through a IMU sensor, which is the MPU6050 through the I2C protocol. And adversarial and attacker can gain access to this I2C channel or to the sensor itself, wherein he modifies the sensor in order to feed the input to the system. Or a second example I have with me is an image classification use case where ESPI is used to, in this case, only to stream videos over Wi-Fi to another microcontroller or processor. In this case, we use a Raspberry Pi, and an attacker could then gain access either to the device, the ESPI itself, or to the protocol, in this case Wi-Fi, that is used to gain access to the interface. The attacker, after gaining access to this interface, performs the model extraction attack, the framework of which that I showed you. The attacker, the computer vision task that was deployed had an original model accuracy of 99%. And the attacker subjected this particular, let's say the AI model using random input attack vector. So we use these random vectors, like I showed you, the Gaussian noise for the image. Multiple of such images are used in order to create a learned data set, and a replicated model is trained, which has the accuracy of 88.9%, which is more than 80% of the original model. We test this extracted model accuracy using the same test data that we had originally used for the original model for comparison sake, and we can already see that the relative accuracy is greater than 80%. Similar is the case for gesture recognition. We create random input attack vectors, this time for time inputs, sensor inputs, and feed that on the I2C channel into the ESP32 hosting the AI model. And this is the original model accuracy, which was about 92, and the stolen model or the extracted model accuracy was over 70%. So in these two scenarios, we can already see that with simple attack vectors such as random input, the attacker is able to extract the functional model. With more intelligent attack vectors, the percentage of the extracted model accuracy, we have seen that it significantly goes up. On the other kind of attack, in this case for time series classification that was deployed on the ESP32, the original input being the signal in orange the original input being the signal in blue had an original class output of slope. Now, with calculated perturbations added to this, which are in this case very indistinguishable, and that is the case in most cases. Even an image we have seen, also in time series, it is indistinguishable from the original input itself. With this adversarial input, we see that the output class is not the original class anymore. It is now misclassified as a different class. How do we go about this? So we added less than 1% of the signal amplitude as the maximum perturbation in each of these axes. We call it the attack strength. And then we calculate the attack efficacy, which is the total number of misclassifications over the total number of test samples. And more than 80% of the adversarial inputs were then misclassified. With increase in this signal amplitude, then this number goes about 96%. And then you will see that the adversarial signals are slightly moving away from the original samples, but the number of misclassifications significantly increase. So in summary, we have looked at model extraction, model evasion, and also some of the other attacks. So in model extraction, we have seen that the AI on tiny devices or the tiny models itself can be extracted with lesser number of queries than large models. And in the model evasion cases, the adversarial inputs can be crafted to evade the tinyML model, and in most cases, the perturbations are indistinguishable from the original inputs. Once the attacker has access to the model through model extraction, he then can compound the effect of having the model with other attacks such as membership inference, sponge attacks, and so on. Now that he knows what the functional model looks like, he can then craft other attacks following the model extraction itself. So also to the fact that the tiny machine learning models or the tiny devices are available to the attacker as such, the hardware attacks together with the software attacks make it more prone to AI attacks. The AI model being stolen and using other information to extract either the information or to misclassify or to cheat the AI model that is deployed on the device. As we have seen in these cases, we do not look into, or the traditional embedded security aspects do not suffice, or they usually cannot detect these sort of attacks on AI systems. With minimal effort, the communication ports or the sensors or the sensor itself can be used to input adversarial inputs to the AI model and hence extract the model. So far we have looked at how the different attacks translate from the adversarial ML, and specifically how they are predominant in the tinyML domain, and how the traditional embedded security would not completely cover the overall umbrella of how the attacker operates in the AI domain. We come into the need for the security for tiny machine learning. Some of the ways how to deal this is to first understand these attacks and to defend them. And defending them comes in two steps: to detect and to act accordingly. So in the analyze phase, we have seen that how we could use some of the attacks itself, for example, model extraction, to understand what is the extraction of accuracy, what is the functional equivalence of the extracted, replicated, or the stolen model. And in an evasion attack, what changes on the input should an attacker do in order to get more attack efficacy and so on. So those metrics help us in the analysis phase. Using this informed information, which is the vulnerability understanding, we can then go into the defense part, where the detection involves usually an AI-based detection or a statistical analysis if we know what is the IID-OOD distributions. That's one way to do it, for example. And once that part is done, so once we are able to detect, then we can use AI itself or the traditional embedded mechanisms to then act on how we want to proceed with this. For example, the first thing would be to have an event debounce to see, to confirm if this event is occurring in a given sequence in a given scenario. Then use the system's tampering detection from the classical embedded security to take the actions, such as any action that we would take when a tampering is detected. Use readout protection to shut off the application software itself, software isolation, and in worst cases, in very critical cases, the system shut down itself, being one of the measures to act to defend the overall machine learning running on these tiny devices. So that brings me to the end. Once again, I want to emphasize the need for the security for tiny machine learning and tiny devices as such. Thank you.
Thank you so much, Yuvaraj, for showing us different examples and different kinds of attacks and criteria to look for. We have a question from Muralidharan Chinnakrishnan. Just curious, how does one train the model considering these potential attacks? Do we consider different training schema, if I could call all together?
Traditional training, yes, of course, does not take this into account. And in most cases, what happens is that the model is trained and then the security aspect comes in, and it is not always possible to retrain the model now for security enhancements. And the most preferred or the most suggested way is to, given a model that is trained and then there is a defense model, for example, the AI informed defense that sits in parallel or in series with the original model, is running in real time together with the original model, and on the field it is able to then detect these these attacks on the system itself. So, and when the defense model sits in parallel, then also the constraints such as inference and so on are taken care, and the defense model takes the same input that the original model would see and detect these mechanisms or these attacks.
And we have one last question. Have many adversarial attacks happened in the industry for tinyML systems or not yet?
We do not know yet. So, and that is why we are running these experiments to see how weak or strong systems are. And that depends on various factors, including not just the model itself, the number of samples used, how balanced are the classes when the models were trained, and what are the other what is the dynamic range of the sensor, for example, and how much is the attacker able to reproduce and so on. So bringing this into multiple perspective, we have not directly said, okay, this belongs to this particular attack, but this is a spectrum, and the need is that we upfront prepare ourselves with these security mechanisms that such that when machine learning models are in the field, that they are protected.
Thank you so much, Yuvaraj. It's an awesome session. It's very enlightening. I'll pass it back to Dr. Nick.
Good. Once again, we want to thank our sponsors, Tiny Edge Impulse, one of the leading what's called platforms for Edge ML and using tinyML applications. Our executive sponsors, Qualcomm, who have advanced AI research to making efficient AI ubiquitous, both hardware and software. Cintiat, accelerating your edge compute. Platinum sponsors, DeepLight, fastest video analytics solutions on ARM CPUs. Kilkatech, global IoT solutions. Renesas, basically big ideas for every space. The Sony Semiconductor Solutions Corporation. Gold sponsors, Analog Devices. ARM, who also have their own talks, so please feel free to sponsor them and jump onto their line as well. PhotoHub, making over-the-air firmware and model updates simple and accessible. That's probably one of the key things moving forward, so have a look at PhotoHub. Microsoft, for their edge capabilities and technologies, including all their, I guess, Azure services to support tinyML. NXP, together accelerating breakthroughs that advance our world, a great hardware provider. SenseML, analytics toolkit suite to be able to do your AutoML capabilities. STM Microelectronics to provide extensive solutions to make machine learning easy. Synaptics, engineering exceptional experiences. And then a list of silver sponsors, including AIZip, Aeon Devices, EMSA, Greenwave Technologies, Gravity Inc., IBM, Imagimob, Etermis, Nota AI, OctoML, Prophecy, Quexo, Rexon, SAP, Silicon Labs, Stream Analyze, TDK and Vincent. So thank you once again for attending. I hope to see you tomorrow online to listen to some of those interesting presentations. And thanks to everyone. See you soon.